All right, good morning. Welcome back. Happy Monday. We'll start by taking our quick look at the calendar. Today, January 30th, project number 1 was assigned last class and it's due this coming Friday. Project 1 is due on Friday. Today, we're going to spend our second of 2 review days. Today, we will review the definite integral. And then in theory, the stuff after today is new, like Calculus 2 stuff and not Calculus 1 stuff. Any questions on the calendar? Okay, so a few logistical things before we jump into the math today. Number one, I just wanted to point out a couple of things on our Moodle page. If you don't have access to our Moodle page, talk to me and we'll make sure we can get you in. But inside of our Moodle page, you'll find a bunch of stuff, including this folder called Notes Packet Filled In. And if you go into that folder, you'll find a couple of PDFs. You guys are section A and my other class is section B. And if you click the PDF, you will get a full color view of everything that I wrote in our big packet the other day on Friday. Okay, so you don't need to furiously copy everything that I write down up on the board. It will always be there in PDF form. I typically post that on Friday afternoons. If you need it more often than that for some reason, you just let me know. Another resource available on our Moodle page is this playlist of class YouTube videos. I record all my videos just like I did last semester. Here's the video from Friday's class. So if you miss a class or if you need to see something again, you can always go check it out on YouTube. Any questions about either of those things? Okay. All right, and then something else I wanted to chat about before we jump in again on page 21. So the very last project of Calculus 1 was a project where you guys reflected on the semester, and in particular, you gave me some feedback about the course and my role in the course. And I sort of furiously wrote down lots of notes based on your feedback, and I have responded to your feedback by making some changes in this class. And so I just wanted to bring a couple of those changes here to you guys. So first of all, a few folks, more than a few folks, talked about how last semester the projects contributed quite a bit to their knowledge of the course, but that they felt that the projects were not weighted nearly enough relative to how much time and effort you guys put into the projects. And so just to remind you, this was our syllabus from last semester from Calc 1, and this was these were the ranges for how you could choose your grading option. And so the projects were worth between 10 and 20%. And somebody pointed out that even if you max out the projects here, and there were 6 of them, that one project was worth a fifth of one test. And it just felt like, given the amount of time you guys put into those challenging projects, that was not enough. And so here's our grading options for this semester. We've got 2 choices. In both of them, you'll notice that the projects are worth 25%. So a quarter of your grade this semester is going to be based on those projects. And I bumped that up based on the feedback I got from you guys last semester. Several folks also talked about how, on the one hand, it was nice to have a bunch of freedom to choose like what grading option would best be most appropriate for how you want to spend your time preparing and studying for Calculus 1. But a number of people also found it quite stressful. Having too many choices turns out to be difficult for our species, and a lot of people felt like they were worried they were going to make the wrong choice, and they wanted to make the best choice to maximize the grade they would get, and it was stressful to not just have the teacher say, here's how I am grading you, don't worry about it. And so to that end, I have come down from a number of options that I gave you last semester to 2. They are called homework counts and homework doesn't count. They are nearly the same. The final exam is 20% for both. The tests are worth either 46 or 51. That 46 and that 20 add up to 66. Quizzes are worth 4. That adds up to 70. So 70% on tests and quizzes in the final. And that is probably just about the bare minimum that I am comfortable doing in any class. So I've kind of minimized that to as far as I'm willing to go. And then 25% for the projects for both options. And then the only difference down here at the bottom is your homework can count for 5% or your homework can count for 0%. And the other change was up here in the tests, okay? So it's just a question of how you want to play with that 5%. Do you want it to be added to your tests, or do you want it to be your homework? Even if you choose the homework doesn't count option, I strongly encourage you to do all of the homework, at least like enough where you feel like you've done some of every kind of problem, okay? All right, you don't need to tell me which one of these you are going to choose until after the first test. I also want to point out another change that I've made in terms of the quizzes. You can see over here the quizzes were worth between 5 and 10%. I have brought that way down to 4% for each option. Last semester, the quizzes were open resource except for other people. And so it was open book and open calculator and open internet, anything, just not other people. And I thought a lot about that, and I mentioned this last semester too towards the end, and I felt like given that the tests were a very closed resource, having the quizzes be open resource was kind of leading to a disconnect, and some people were doing awesome on the quizzes and not awesome on the tests. And so what I've done is made it so that this semester the quizzes are going to be pretty much closed resource, just like the tests are. And I brought the percentage on these quizzes way down to try to make it so that the quizzes really are aligned with the tests, but they are a low stakes way to get feedback as you are preparing for each of the tests, right? More about the quizzes in a future class. Somebody recommended, the quizzes are all take home this semester, just like last semester. Somebody recommended increasing the suggested time on the quizzes. I had a little recommended time limit, but that you could take as long as you want. That's still the case this semester, but I have increased the suggested time limit. A number of folks wrote that they were glad that the number of homework problems got reduced. I did that last semester in the middle of the semester. I did it this semester right before I handed out the syllabus. So if you are curious as to what the old homework assignments were, you could compare this page to the last page on your syllabus. I'll put that up there. You can check it out after class if you're interested. All of the homework assignments got cut. Some of them got cut quite a bit. Okay, a few folks wanted to know if you could rotate tables during the semester, and the answer is yes, absolutely. You can sit at a different table every class if you want to. I think it's great to get to know other folks, especially because most of the people in this class are taking other classes together this semester and will do so again next semester. So definitely move around and get to meet some new folks. And then the only other thing I wanted to mention here has to do with notation. And a number of people find that I am quite picky in terms of notation and taking points off. And it's okay for you to make eye contact with me here and smile, because this is like something that like half of you mentioned in the project. And so I want to say a couple of things about why I do what I do, and then something that, and then a change that I'm making this semester from last semester. So first of all, most of the people here are in STEM field. STEM is science, technology, engineering, and math. And so being able to communicate effectively is super, super, super important in the STEM fields. And so notation, part of the idea of notation is to help you communicate effectively. So it's not notation for notation's sake, and that's not why I'm taking points off when the notation doesn't agree with like what is mathematically correct. It's fundamentally about communicating. And so I still want you to use notation correctly, and I still am going to be looking very carefully at notation. But I think that my minimum number of points off for like notation errors last semester was a -1, and a -1 on a 5-point problem is 20%. And I think that probably some people felt, and justifiably so, that the percentage that I was taking off for these little notation things didn't quite jive with the importance of the notation error that was happening. And so what I've decided to do, I'm still going to look for good notation, and I'm still going to put a little, like minus something when I see a problem. And that's just my way of saying like, hey, look at me, I need you to make a small change here. But I'm now going to be open to doing like half points off, or maybe quarter points off, and just something where you're not going to feel like there's this cumulative thing happening where the grade on your test doesn't really reflect your knowledge of calculus. It's, it just reflects that you lost a bunch of points on notation stuff. So still going to try to get your attention with those little minus halves and minus quarters, but hopefully you won't feel like it is way out of whack with the value of the errors that are being made. Okay. So I think that is that. Thank you for bearing with me through that. All right, let us jump in again on page 21, and we'll start doing some calculus. Okay, our summary. In this class, we review the definite integral in the first part of the fundamental theorem of calculus. There are two parts of that theorem. We also explore some contextual interpretations of the definite integral. That means word problems. Okay, so moving on here, we're going to jump to number 1. It says, let's use technology to find the integral from 0 to pi of sine of t dt. Okay, so technology for me is going to mean oftentimes a graphing calculator. You do not have to have a graphing calculator this semester, but if you have one, go ahead and take it out. It's also okay if you have an app on your phone. It's also okay if you have nothing at this particular moment. So looking to try to find the value of this integral. So there are two ways, two things you need to do to get your computer or your calculator to look right. So you're going into math, which for me is over here on the left-hand side, and you're looking for the thing that says FNINT. It's way down near the bottom, number 9 on my machine. And I hit enter. So for me, it just says that. I've got the old operating system on mine. Yours might look slightly different. So either if you got the new OS, you make yours look like this first one, or if you got the old OS like mine, you make it look like that. So again, sine of t from 0 to pi. So sine of x in our case, comma 0, comma pi. You're in the y equals. Yeah, you want to be on the home screen there. Okay, and so we ask the calculator for that. And what did I do wrong? Go to x. Thank you. Right, got to tell it what the variable is. Sine of x, comma 0, comma pi. 2. Anybody get anything other than 2? I'll do something really funny here for a second. Okay, so I'm typing in exactly the same thing here. I made one small change. Some of you might have caught it. Yes, I did. I did not close the parentheses, but the calculator doesn't care. Okay, so I got this 0.086. That's in degrees. All of calculus is in radians unless specified otherwise. The integrals are not the same. So make sure when you walk through the door to this classroom, you get your calculator in radian mode. This is especially important if you take physics this semester because I think a lot of physics is in degrees. So you end up kind of going back and forth. Okay, so the integral is equal to 2. So let's come down here and take a look. And if you have any issues with the calculator, I can walk around a little bit and help you figure that out. So the value of that integral is 2. What does that integral represent in the given graph of f of t equals sine of t? From 0 to pi, area under the curve from 0 to pi. And I think pi is right there. Is that right? To the x-axis, right? It's the area between. I know we often say under, and I will sometimes say under too, but I really should be saying between, right? It's between the sine function and the x-axis. And then going to 0 to pi, which happens to be the x-intercept there. Okay, so the area inside of that one hump of the sine curve is 2. And even though I know that and I've known it for years, it still surprised me. It should not be that nice, but it's 2. The units on the 2. The one box here is 1 square unit of area. I mean, it's square units. It's not 2 radians. No, it's an area. It's 2 square units. If my graph paper is in inches, then it's 2 square inches. Yeah. Okay. So there is a kind of a review of some integral stuff down below. I think that there's just a little bit too much vocabulary and notation floating around. We're going to speed through this thing here. So that integral, like we just said, represents an area. over an interval a to b in this case. The a and the b are called, remember the word? Starts with L. Limits. Those are the limits of integration. And the function itself, f of t, that's got a name. It's called the integrand right there. And that dt right there is just an important piece of the notation. It's supposed to represent the width of a rectangle. You got to write it even though it really doesn't contribute much mathematically. Okay, and so last semester, or when you took Calc 1, you probably ended up looking at a picture something like this, where you were drawing rectangles. And so, for example, let's take a look at this first interval. And suppose that we use the right-hand endpoint to determine the height of the rectangle. So that means that we go to T1, we go up to the curve, and then we're going to complete that thing to a rectangle with that height, which means going to the left and then going down. And in the second interval, T1 to T2, again, we're going to pick the right-hand endpoint. We're going to go up to the curve, and we're going to use that height to determine a rectangle left and then down. And I'll just jump all the way to the end, right-hand endpoint, left, and then down. And the idea is that finding areas under curves is hard, but finding areas of rectangles is easy. And so we just start by making this easy. We draw a bunch of rectangles, and then we add up the areas of those rectangles. And so we had all of this, these things here called Riemann sums, and we ended up using something called sigma notation. I'm going to skip it for right now. And on the next page, we've got this picture that's supposed to illustrate what happens as you use more and more rectangles. You get more accurate. That's the idea, right? And so fundamentally, how many rectangles do we really need if we're going to talk about the exact area under the curve? Like all of them, infinitely many, right? Like you can't stop at a bazillion rectangles because you'll still have a little bit of area there. Plus bazillion's not a number. So we use infinitely many rectangles, and so we've got this crazy complicated looking thing here, which just represents find the area of the rectangles, add them all up, and let the number of rectangles go to infinity. But we just don't feel like writing that over and over again, so we just abbreviate it, or I guess represent it with that notation, okay? So that thing right there is called the definite integral. You see it, and you say, oh, okay, infinitely many rectangles, it just represents area under the curve. Nothing more, nothing less. Okay, let's take a look at number 7. And first I want to say there was like a graphical glitch here in number 7. The two bold lines were supposed to just be landing right on the axes, but somehow they got shifted a little bit from the picture. So looks like there's like 2 axes here. That is not right. It's just supposed to be X and Y axis. So it says the graph of f prime of t is given below. So that's this guy here, f prime of t. And it says this is the graph of the derivative of f, not of f itself. And we're going to find the integral from 0 to 4 of f prime of t dt as accurately as possible. So we know every time we see a definite integral, it just means area between the curve and the x-axis. So that area is broken down into a few familiar looking shapes, right? We've got purple triangle, and then we've got red triangle, and then over here we've got blue triangle. Good? And so that integral is just saying find the total area between the curve and the axis. And fortunately, it's triangles, and we can find areas of triangles pretty easily. So we will, yeah, good catch. All right, let's start writing in some areas. What's the area of the purple rectangle? 1, right? Half the base times height. Area of red, also 1, right? Half the base times height. Area of blue, that's a half. Half there, and red was a 1. Okay, so if we really just wanted the total area, we add up those 3 numbers and get 2.5. But we've actually been lying to each other this whole time because the integral doesn't just represent area, it represents signed area. And so as Sephora points out, anything below the x-axis, how do we deal with that? we just subtract it, okay? And so it's true the area of the red triangle is 1. In terms of that integral, it counts as a -1.
So if this were for the test question, we're asking for a find the integral, you would subtract below the x-axis.
Yes.
You were saying
find the total area. You'd add them all. Right. Area is always positive, but integral includes negative signs. Okay, so the value of this integral is a +1 in the purple, and then a -1 in the red, and then a +0.5 in the blue. So that integral is half. Okay. Okay. And then we've got this detour here in number 8. You should have seen this theorem before. Fundamental theorem of calculus, part 1. Says if f prime is continuous on an interval a to b, then the integral from a to b of f prime of t dt is equal to f of b minus f of a. The integral of the derivative is the change in the original function. So we talked about this very late last semester. Hopefully it looks familiar. It's going to be really, really important for us. In English, it says the definite integral of a rate of change is the total change. Rate of change, we know, is a derivative. So when you do a definite integral of a derivative, you get the total change in the actual function, the original function, not the derivative. So it's important to notice it's an f prime inside, just plain old f's out here. Okay, number 9, let's refer back to the graph in question 7, and we're going to assume that f of 4 is 2. Remember, that is not the graph of f. What is that the graph of? That's f prime. Okay, so f of 4 equals 2 is brand new information that we did not have before and that we could not read from the graph up above. There's no way to get this information. But if it's given to us, then we can use it to find f of 0. Let's give it a shot. According to this theorem right here, I'm going to write the integral, and I'm going to put 2 specific t values here, the only 2 t values that I either am given or I care about. One of them is 4. The other one is 0. One is given, one I want. So that dictates that I'm going to use the numbers 0 and 4 here. And we'll see why those are important to put there in a second. That's a little f prime. This is a capital F prime. Otherwise, it's the same. And it's equal to f of b minus f of a. So in this case, f of what? F of 4 minus f of 0. Notice the order is always the guy on top minus the guy on the bottom. Okay, f of 4 was just handed to us. What is it? It's 2. F of 0 is the thing we want, so I'm quite content to copy that there. If only I had a value for the whole left-hand side, then I would just be a simple equation to solve. But that integral just represented the signed area, which we've already calculated. What is it? It's 1/2. And so that's the easy equation that we solve. And hopefully now we see why 0 and 4 were the right numbers to put up there. All right, you can put any numbers you want, but on the right-hand side, one of them better be the thing you were hoping to find, and the other one you better have been given. Okay? That's why 0 and 4 go on the integral. Yeah, so for me, it's the right-hand side dictates, right? Like one of them is what you want, and the other is what you know, and then the left-hand side, hopefully we can calculate based on some other information. If what went to 5? Yeah, exactly. So like if it happened that we calculated from 0 to 5, that wouldn't be useful for us in this one. Yeah. So hopefully the integral that pops out is one that you can calculate some way. And in this case, we calculated it by triangles, but in another case, like maybe you have the formula for f prime and you just type into the calculator, math 9, just like we did before, right? So there's different ways to calculate this definite integral. Okay, so let's get our answer, and then this one will be done. So we subtract the 2. And so therefore f of 0 is positive 3/2. Is that okay? Okay. All right, so we've got 45 minutes. This is a very robust activity, so see how far you can go. motoring all the way through.